This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Okay, let's get cracking, shall we? It's just saying I think we're going to finish a bit earlier than normal today, so that would be nice. So these pictures, I'm not going to talk about them all at all, except to say that they're from the Gallery of Fluid Motion at the Physics of Fluids Journal, Brock and Co. Who else? Nobody else. All right. Look at that. That's from a fish swimming. Isn't that cool? All right, but I'm not going to talk about them. So you can see all pretty fluid pictures at the Gallery of Fluid Motion. Anyway, let's make that go away. Okay, so we're going to do two examples now of finding centres of mass of objects that are either added together or have bits cut out of them. Okay, here's the little formula that we're going to use. So these little things, each of these things normally requires a calculation to be done. Okay, if you don't know what it is already. If there's an exam question or a assignment question, I make it very clear which ones you can use a formula for, like a sphere is 4/3 pi r cubed or whatever, and which ones you have to actually do by integration. We're going to do this example here. The next example is, oh look, I've changed the example. Oh, I thought I didn't. Is this the example that's in your notes, example 7? Yes or no? 7. Pardon? Yeah, what's number 7? Oh, the same as that. Okay, it used to be another one which I don't like doing, so I changed it. Oh, there you go. All right, so we're going to do this example and example 7. Before we do that, though, this other page in between, you know how when you're calculating the volume or the area of a two-dimensional body, you can calculate it using horizontal slices or vertical slices, and one is going to be easier than the other, and you can choose, right? When you're doing centres of mass, you're not allowed to choose. You have to do it a certain way, and it could be that that certain way is the way that gives you a really tough integration, okay? Now, by using this addition of centres of mass thingo, you can actually do the integration the easy way and get the right answer, but you have to do a few tricks, okay? This tells you how to do the tricks, and I'll put an example online that shows how to do the tricks, but we're not going to do that in class, okay? But that's how to do the tricks if you want to do the integration the other way, but you're not supposed to. Okay, all right, so we're going to do these two examples now. This thing here. Taylor says, why are we doing this shape? Because it's very... Okay, the reason I'm doing it is because it's really hard to write examples that we get an integral we can actually do. And here is one of them. Okay? Although in this one we're not actually going to do an integration because we know everything already. Okay. Consider a sphere of radius r, so this distance here is r, radius is r, with a conical hole cut in it, and the cone has got a radius of a with a height h. Find the centre of mass. Okay? The centre of mass for something like this is going to be somewhere down here because that's where all the mass is. Right? It's not going to be halfway, it's going to be underneath halfway. It's also going to be on this axis here. Okay? And we're going to say that we know that. So the centre of mass in the x direction, which is forwards, is 0, and the centre of mass in the y direction, which is sideways, is 0 as well. And all we're going to do is calculate the height of the centre of mass. Okay? All right, now the formula that's on the sheet says you just have to do the volume times the centre of mass and add up those things or take them away for the different shapes, right? So the volume of the body times by the centre of mass of the body is equal to the volume of the sphere, centre of mass of the sphere, minus, because we're cutting it out, the volume of the cone and the centre of mass of the cone. Okay. So this is the formula that you have to use because you can only add the integrals, right? You can't add the centres of mass, you can only add the integrals. So you have to do the volume times by the centre of mass. Okay, now let's have a look. the centre of mass of a cone, we just figured that out in the last example, right? We know that it's a quarter of the way up from the bottom, so we can use that to find this. The volume of a cone, we also found that out as well. Centre of mass of a sphere by itself, well, that's kind of easy. It's in the middle. We can figure that out. The volume of a sphere, well, we know that. This is the thing that we have to find. And the volume of this whole thing with that cut out, well, we can figure that out because we're clever as well, okay? So we know all of these things by integration or otherwise already, and this is the only thing we don't know, okay? So let's write down what each of these things are. Oops. For the sphere, the volume of a sphere is 4/3 pi. Now this sphere is a big R cubed. All right, now the volume of a sphere and the volume of a cone are not something I would expect you to remember. If I'm allowing you to use them already without integration in the exam, I'll give them to you, okay? So don't think you have to memorise those kind of things. All right, the centre of mass of this sphere is at z coordinate what? No, zero's down here. No. Here, right? R, yes, it's R. Right? R is the radius of the sphere, so this distance here to the middle must be R. Okay, so that's all we need to know about the sphere. The cone. The volume of the cone, well, we just did that, 1/3 pi radius squared, so that's going to be a squared times by the height, h. Centre of mass of the cone. Centre of mass of the cone, where's that going to be? What's the z coordinate of that? Think. Quarter R, that's going to be, here's R, right? A quarter of R is going to be here. That's not the centre of mass of the cone. Almost. Pardon? 3/4 H, but minus 3/4 H, that would be down here. Not Z. You're nearly there, you're so close. What's that point there? 2R, yes, 2R. That gets you to there. Now the centre of mass, yeah, minus 3/4 H, that's right. So the centre of mass of a cone is a quarter, so to get to there you would do minus 3/4. Okay. You can have a lolly for figuring out the hard bit. That's very far away. Oh, my muscles are too big now. I was doing all right before. Okay, so now we know this, we know this, we know this, we know this. All right, we just have to figure out this. Let's put over here. Well, the volume of the thing is going to be the sphere minus the cone, right? So 4/3 pi r cubed minus pi a squared h. All right, so now we can just put everything into that big formula. Take away 1/3 pi a squared h. All right, volume of the sphere. Centre of mass of the sphere minus times this one. Make sure you use your brackets. Oh look, I'm nearly going off the page already. Okay, now when you're doing these problems, we just want to write z body equals, right? When you're doing these problems, you can never really do much to simplify them nicely. You can do a little bit. In this case, we've got a pi everywhere, right? So we can cancel out the pi's. 3 3 and a 3 and a 3 and a 3, and everywhere we've got a third, right? So we can cancel out the thirds. And that's about it. That's all we can do. So you just take this and you just write it a bit more neatly. Z bar equals, so it's going to be 4 r to the power of 4 minus a squared h divided by that's it. That's about as good as it gets. That's it. So these things really neaten very nicely. You just have to neaten them as much as you can. And it's really hard to check whether you've got the right answer, right? If you had spare time on the weekend, what you could do is put in some values for A and H and R, and you could actually calculate this and see if it ends up to be something sensible. But you can't just tell by looking at the formula. It's not that straightforward. All right, does anyone have any questions on that one? No? So the moral of the story here is make sure that when you're adding things together, you're not adding them just the centre of masses. Okay, don't do this. This won't give you the right answer. Make sure you use a formula like this. Okay, add them or subtract them, whether they're adding on or cutting out or whatever. And then that's what you do. Okay. All right. So the other example 7, where I was talking about before, I'll put that online. Oh no, that's this one. Let's not do that one. That's too hard. Let's do this one. This is the one in your notes as well. Okay. Find the centre of mass of the upper half circle. Centre 0, 0 and radius r. All right. So the first thing to do with this one is to draw a picture, right? Because I haven't been so kind enough to draw us one. That's not too bad. Okay. Okay, centre of mass of the upper half circle. Here's a circle and it's the upper half of a circle. It's got centre 0, 0 and radius r. Okay. All right. Let's say that we're clever enough to know that the centre of mass is going to be somewhere on this line, and on this line, x is equal to 0. Okay. So the centre of mass in the sideways in the x direction is going to be 0. Okay, and we're just going to find the height of that centre of mass by integration. So this is one that we don't know just by looking. Okay, it's a flat thing, it's a circle, not a sphere, right? So that means we do 1 over the area. Okay, we're in the y direction, so we put a y here, and it's got to be dA as a function of y. Okay, now we don't get a choice about which way we're going to slice it. We have to slice it so that everywhere in a slice has the same y coordinate. Which way will you slice it so that everywhere in a slice has the same y coordinate? Horizontally. Yes. You're going to slice it horizontally, and think about that. If you slice it horizontally, then everywhere in here has got the same y coordinate. Okay? If I sliced it vertically, this point here has got that y coordinate, this point here has got that y coordinate, this point here has got that y coordinate. And everywhere in this slice has a different y coordinate, right? Don't slice it like that, you'll get the wrong answer. If you slice it this way, all of these points have got the same y coordinate. Okay, that's what you have to do. That's the rules because of this y here. Yes?
If you do it the wrong way, is it like spectacularly obvious that you've done it wrong?
What will happen is when you come over here to write we want to write this in terms of y, you won't be able to do it. And then you won't know, well,
Will you be able to
maybe you'll know that I can't do it because I've done the wrong thing, or maybe you'll say I can't do it because I just don't know what to do, right? So when you get here, you won't be able to do it, and that will be the problem. Okay, so everywhere in a slice has to have the same same y coordinate because it's a y one. Okay, I mean the easiest thing to do, right, is to draw your slice and think about the different points. Do these have the same y coordinate? Yes. If they don't, then that's trouble. Okay? Thinking about it in your head's harder. Just draw it and then you'll be able to see. All right, slice horizontally. Okay, we're talking about a flat area now. So the shape of the slice is going to be a rectangle. It's going to be this distance times this distance, right? The base times the height, because it's just a rectangle. What's this distance here? Tell it to me in any of these letters that you like, but what's this distance here? Pardon? Almost. This is R from here to here. This point here has coordinates x, y, whatever they are. What's that distance there? Pardon? 2r. It's not 2r because r's all the way out to there. 2x. It's 2x. You've had a lolly. This is the x coordinate here, right? So that distance is x, and this is the same, so it's 2x's. Okay? Cheeky, yeah. 2x. The height of it, that's a bit easier. Little step in the y direction. Okay? So that's my area. This here is telling me that we're going to integrate with respect to y, which is good because it matches up with this y here, right? Which it has to do. If it doesn't, then you're in trouble. There's another way, Taylor. When you get to here, if this thing is not matching with this y, then it's wrong, right? They have to match because that's telling you to integrate with respect to y. And you've already got a y there. Better match up. Okay? All right, now we have to change this x, though, into something in terms of y. The 2's fine, that can stay. But the x can't stay. How are we going to join, how are we going to match up the x and the y? Trig? Pythagoras. Beautiful. Pythagoras. This distance here is y, is r, right? This distance here is y. This distance here is x. And you can use Pythagoras. The other way to think about it is, we can use Pythagoras to join those things together, because r's a constant here. The other way to think about it is, this is a circle, right? What's the equation of a circle on the origin? Nobody knows. Yeah, x squared plus y squared is the radius squared. That's exactly Pythagoras, right? X squared plus y squared is r squared. The equation of a circle and Pythagoras, they're the same thing. Okay? Isn't that amazing? X squared plus y squared is r squared. By Pythagoras or by the equation of a circle, that means I can change, I only want x, right? Not x squared. That means I have to deal with the square root, which is a bit of a pain. R squared take y squared dy. Now this is in terms of y, so that's fine. R is a constant here. It's the radius of our circle, and 2 is a constant, so that's fine. Everything's ready to go. Y to r squared take y squared dy. Okay, we're integrating with respect to y, so we need to put some bounds on our integration. We're integrating with respect to y. What's the smallest y and the biggest y? 0. And what's the biggest one? R. Beautiful. 0 to r. R. Not Pirate Day, is it? Oh, I'll tell you what day it is. Back to the Future Day. 4 o'clock this afternoon. Pardon? That's right. They did make some not long ago. Okay. Now we have to integrate this. How are we going to integrate this? Start with the easy one in first and then work to the harder ones as you go. How are we going to integrate this one? Pardon? Yep, what kind of substitution? Beautiful, you can have Lollybrock. It's a U substitution because... Oh, far out, sorry. Sean, can you get that? No? Oh, sorry. Oh, too strong and then too weak. Okay, it's a U substitution because here we've got a function and here's its derivative. Okay, the derivative of a y squared is a y. Be careful of the 2 and be careful of the minus sign. Let u equal r squared take y squared. Oops, squared. du is equal to minus 2y dy. Okay, so here's a y. Well, you know what? Look, there's a 2 here as well. Let's use that 2, shall we? Here's a 2, here's a y, and here's a dy. 2y dy, so we just have to get rid of the... Oh! du equals 2y dy. 1, because we got rid of that 2 into here. The y dy is going to turn into a u du with a minus sign. And this will be the square root of u. Okay. Easy done. Okay. These are y bounds, right? So either we better say y equals 0 and y equals r, or we better change them to u. I'm going to change them to u's. Y equals 0, u equals r squared. When y equals r, u equals 0. Okay, so this is one of those integrals that looks funny because you've got a 0 up the top, but actually that's because of this minus sign. Those two things will kind of cancel each other out. And now we can integrate. Okay, so this is like u to the half, so you increase the power by 1. 3 halves, 2/3 comes out the front, r squared 0. Minus, oops. Alright, if I put an r squared into here, the squared and the half here are going to cancel each other out. I'm going to get 2/3 r cubed. Okay, now the minus and the minus will cancel each other out. The area here is going to be a half pi r squared. Okay, the area of the whole half circle. The area of a circle is just pi r squared, so we want half of that. And we want it on the bottom line, so we've got a 2 and a pi r squared on the bottom. The minus and the minus will cancel each other out. We've got 2/3 r cubed. Okay, so let's just write that a bit nicer. 4r over pi 3 pi. Oops, sorry. 4r over 3 pi. Okay, so let's have a look at this. First of all, 4 and 3 and pi don't have any units. R has got units of length, which is just what we want because we're finding a distance, right? So the units are right. And if we have a look at our answer, 4 times r over 3 times pi, we can figure something out in our head. Let's think if r was 1, then you'd get 4 divided by, well, that's about 9, right? So a little bit less than a half. Little bit less than a half is going to be here somewhere. That's reasonable. That's it. Does anyone have any questions about that one? No? Let me just check. that's it. We did finish early. That's nice, isn't it? Okay, so that's it for today. Good luck in your quiz if you haven't had it already. Make sure you hand up your assignment tomorrow. I've got consulting this afternoon. If you've got any assignment questions, I'll be in my office, anxiously waiting for someone to come and ask a question. Other than that, I'll see you on Friday.